Okay, so welcome back. We're going to do another rule. This is called the power rule. I forgot to write it down. Okay, so before we did two derivatives. We took the derivative of f of x squared, which gave us 2x, and then we also took the derivative of square root of x, which gave us 1 over 2 times the square root of x. But we can also write this way. The derivative with respect to x of x to the 1/2 power is equal to 1/2 times x to the negative 1/2 power. So if you look at this one and this one, you might start to see that there's a pattern develops. Okay? So what we're going to do is we're going to develop the power rule based on any positive power of x. Okay? So now what we're going to do is we're going to develop this for the positive exponents, positive integer exponents first, and see if we make a generalization, see if there's a generalization for that case, and then later on we're also going to look at and show that this also works for the negative exponents as well, and so then we're going to develop the general power rule. But for the time being, let's just stick to positive integers of positive integer exponents. Okay, so let's look at another one and see what pattern develops here. So let's take the derivative. Let's take f of x is equal to x cubed. And let's see what happens when we apply the difference quotient and taking the derivative. So f prime of x equals the limit as h approaches 0 of what? It's going to be f of x plus h minus f of x over h. And so now if I just apply this, I get the limit as h approaches 0 of what? It's going to be x plus h cubed minus, f of x over h. And this is going to equal the limit as h approaches 0 of what? Well, oh, I'm sorry. Hold on. I'm losing track here. This should be x cubed. Okay, so now, as before, all we're going to do is simplify this. So since this is a cube, okay, remember how to do cubes. Again, this is going to be x cubed plus 2 hx squared plus 2 h squared x plus h cubed minus h cubed, right? Wait a minute. These are the ones, right? That's these are 3's. Okay, so now, obviously on the bottom we have h. And so, as we've seen before, these are going to cancel. And then we can factor out an h, right? So this is going to be the limit as h approaches 0 of h times. And then we're left with 3x squared 3hx over h, and the h's cancel. And then if we take the limit of what's left over as h approaches 0, this term and this term are going to go away. And so we're left with 3x squared as the derivative function. Okay, so notice that we started with x cubed and ended with 3x squared. Notice here when we started with x squared, we ended up with 2x. And over here, we started with x to the 1/2, and we ended up with 1/2 x to the negative 1/2 power. Okay, so notice the pattern. It looks like, and again, be careful because we normally would not just generalize based on examples, okay? But in this case, what we see, what seems to be happening is the exponent on the original function becomes the coefficient of the derivative function, and the exponent on the original function decreases by 1 on the derivative function. So it seems that the rule is that the exponent drops down to be the coefficient, and then you decrease the exponent by 1 to get the derivative function. Same thing here. The 1/2 comes down as the coefficient, and then we subtract 1 from the exponent, and we get this. Likewise, it sees the same thing. We take the exponent down to be the coefficient, and then we subtract 1 from the exponent to get this. And so that's what seems to be what we're going to call the power rule. And in fact, that is the power rule. Okay? And so next video, what we're going to do is we're going to introduce the next theorem, which is the power rule, and then give a proof and show that it's true for all positive values of the exponent. Okay, have a great day.